15.1, using linked lists. So we're starting chapter 15, Introduction to Data Structures. Alright, so a linked list is a data structure used for collecting a sequence of objects, and the trick about, or the key for linked lists is that it's very efficient as far as the number of steps required to move something, add or remove something from the middle. It's not very easy necessarily to pull something from the very beginning or very end of a list, but to insert or delete something in the middle is extremely easy. And the reason being is that a linked list is a number of nodes or sort of independent objects, each of which has a reference to the next one. So you might not be able to access the entire list in one shot, but each one does know where the next one in its list lies. So we said adding and removing elements in the middle is very efficient. Visiting the elements in sequential order is efficient, that is going from beginning to end or end to beginning, because each node knows where the next one is. Random access or accessing out of sequential order is not very efficient, because if I want to go to number 2 in the list, the only node that knows where number 2 is, depending on the type of list, is nodes 1 and 3. So if I am in or sort of viewing node 4, I cannot jump immediately to node 2 because node 4 does not know where node 2 is. It only knows where nodes 3 and 5 are. So here's a basic picture of what a linked list looks like. So first you have your linked list, and it's parameterized of the type. Alright, your actual linked list object, that knows where your very first node happens to reside. Okay, it doesn't know anything else except that this is where my node, my list of nodes begins. Now this is a singly linked list, that is, each one knows where the next one is, but you can't go backward. So the first one knows where the second one is, the second one knows where the third one is, etc. Now here's why inserting into the middle is very efficient. Alright, all I have to do is create a new node. So here's my new node that I've created with some sort of data. This is a list of strings, so I've got a string data Juliet in there. Now originally the Harry node knew where to find the Romeo node. That was the next one in the line, but I want to put Juliet between Harry and Romeo. So what I do is first you have to save how to find Romeo. So you copy Harry's reference, gets copied to Juliet. So now I've got both Harry and Juliet pointing to Romeo. Then I have Harry instead, after I've saved it so I don't lose the data, I have Harry point towards Juliet, and now it's in between. And removing is sort of the same way. If I wanted to remove Juliet, I just have to remove who points where. And then eventually the garbage collector just comes and removes the unused Juliet node object. So linked list class is very generic. I have to specify the type in angled brackets, so you have to give it a parameter. So linked list of products, kind of like an array list or anything, or the parameterized comparable interface we are working with today. It's in the java.util package, so java.util.linkedList. And here's a basic list of some of the methods that it knows how to do. Okay, I know how to make an empty list. I can add to the end of my list. I can add Harry to the end. I can add to the beginning. That's relatively easy as well. Especially if there's nothing in there. I can get the first, which would return the element. I can get the last element. I can remove an element. Now notice that remove is actually a return call. When you remove an element, it does give it back to you. We're not always going to do something with it, but it is nice to know that it's not going to delete the data. So you call remove, you have the option of putting it somewhere to save it. And I have what's called an iterator, which is is another class that knows how to work its way through sequentially through a linked list, so you can get the data without actually touching anything. So my list iterator type gives access to the elements inside a linked list, encapsulates a position anywhere inside the linked list, and most importantly protects the linked list directly from giving you access to see it, but not necessarily directly mess with the linked list. Because if you mess up one of your node references, then you're going to break the chain. You can't find anything. So here's how a list iterator works. I've got my original linked list of strings, which again knows how to find the very first node. The next node knows how to find each subsequent one after it, and that's it. A list iterator has to have the same type. And what it'll do is it can move across from one spot to another. It can start here, it can jump to this one, and it just sort of follows the node reference, so it knows where to find the next one, and all it does is it pulls out the data and lets you look at it. It doesn't actually remove it, and then it moves to the next spot if you want it to. Pulls out the data, lets you look at it. So you can get to the data, and every time its reference points to the next little data piece, and it reads the next node reference to know where to go. So you can think of your list iterator very similar to the cursor on a word processor. So if very first thing I started with was my list of, in this case, 4 names, my iterator starts at the beginning in front of the first one. I call the next method, it moves across, and now it's sitting in between as shown here in this picture. Alright, now if I do an insertion, this is kind of funky. I insert here, and then I move to the end after I insert. I'm not inserting it before where I am. It does start out as here, so here's my iterator between D and H. It does drop a J in front of itself, and then the cursor, essentially the iterator, moves over the one it just added. So the list iterator method of the linked list class gets a list iterator. So linked list string employees will create our linked list, and then we're going to tag the iterator to it. So employee names gets the list iterator that we just created. So then they'll work together. So next moves it over one. Next throws a no such element exception if you're already at the end of the list. It does look ahead, see if there's anything there. Has next returns true if there is something after you. That is, iterator next is not null. The next method returns the element that the iterator is passing. Okay, so it lets you see the data, kind of like the remove. You don't have to do anything with it, but every time it jumps over, it does get the data that's inside of the node. And we do have an enhanced for loop. So for string name, go through employees, do something with that name. I could print it or whatever. The for loop does use an iterator to visit all the list elements. Okay, you don't have to create one at that time. Linked list class is what we call as a doubly linked list. So I know how to go forward and I know how to go backwards. So it stores a reference to the next node and the previous one. To move the list position backwards, you can use the has previous method and previous. Okay. Adding method, this is a little tricky to add. You have to do a lot of updating. You don't want to drop a reference or you lose the list. But it adds an object after the iterator and then moves the iterator past it. So if we're to call the add Juliet, it'll drop the J and then move across. The remove method removes and returns the object that was made by the last call to next or previous. And a few things about remove. You can only call it once after calling next or previous. So I can go next, next, remove, remove. I can't do that because that is 2 remove calls after 1 next call. You cannot call immediately after a call to add. So I can't add and then remove. You have to add and then move the cursor. If you call it appropriately, it will throw an illegal state exception. So only once after a next call, and cannot call remove immediately after add. So table 2, the methods of the list iterator interface. Iterator next, iterator has next, previous, go previous, add, and remove. So the sample program, which is in your Dropbox folder, and also starting on page 669 of the book, generates a linked list, importing it from the util class, adds a few names, and then runs through it. Okay. So public static void main, so it's your main class. Create a linked list of strings called staff. Add at the end Diana, Harry, Romeo, and Tom. So Diana gets added, then Harry gets put at the end, then Romeo, then Tom. So in the comments, the little bar indicates the position of my list iterator. So I have to make one first. That's here, line 19. First I have to make my list iterator, tag it to my staff list, and you can see in this case the cursor's at the very beginning. I go next, it jumps over Diana. Now it's the cursor sitting in front of Harry. I call next again, it jumps Harry and is now sitting in front of Romeo. Alright, next page, I'm going to add Juliet. Remember that it's going to add it between the H and the R where we were sitting. So DH RT, it will add DH J. Oops, let me do that right. We'll have DH J RT, and then after the add, without calling it, the iterator will move. It'll put in your data and then move over. I remove the last. I go next, which means I'm now in front of Tom, or behind Tom in front of Romeo. Remove the last traverse element. So you can think of that almost as hitting the. Sorry, we forgot to add Nina as well. But removing, you can think of that as like hitting backspace. I'm in front. Right here, I'm in front of Romeo. So when I remove the one behind me. Return it if you want, and then print the list. Now, if you notice, there's a typo in your book. All right, it said your book says for string name staff system out print iterator.next. Now, if you just try to run that as is, it's going to do something for you. Okay, so if I try to run that as printed, all right, I get an error. All right, and the error is the fact that no such element. It throws out Tom, and that's it. Well, that's because the last thing we did was removed Romeo, so the cursor is sort of here in front of Tom, and I call print. The iterator moves here and then stops. It can't go anywhere else. Why is that? Well, because the first part of the book uses that for loop. It says for string name sequence through my staff. However, in your book it says print iterator next and keep going. Well, iterator next, I never reset it, so it's sitting right here in front of Nina. It prints Tom and then gets to the end. So we're sitting right here. Tom's as far as it can go. Okay? So you either have two fixes. I can use the name, and I don't even have to make an iterator because the enhanced for loop can do that part for me, and then I can sequence through and print my names. Or if you wanted to use the iterator, you would have to reset it to the beginning, and the easiest way to do that is just to make a new one, because every time you make one, it starts at the beginning. So what I could do is make a new list iterator. We're going to call it I2, tag it to my staff linked list as a list iterator for it, and then for string name staff, I could do it that way, or I could just say, in this case I wouldn't have to do anything, I could print iterator next. So I could do while iterator has next instead of a for loop, and then print the iterator next in a space. Either way will work. I can either print my name, or I can use an iterator, but if I'm going to do that, I have to put my iterator back to the beginning of the linked list. Otherwise, it doesn't know it doesn't automatically back up for you. So you get this as expected. So self-check. Do linked lists take more storage space than an array of the same size? So if I had a linked list of 10 items, is that any bigger physically in the computer's memory than an array of 10? The answer is yes. First off, you need to store the node references. All right, each node is a separate object, and there is a fixed overhead to store each object. Why don't we need iterators with an array? Because each integer index, each spot is indexed and has a number value, and you can use it directly. So an array is good for random access, or access that's not sequential in order, but it is a little tricky to remove things from the middle of a normal array, because then you have to shift everything around, which takes a lot of time.